This question is about a box loaded with textbooks. It has some weight. You're given a weight. It's on a ramp. The ramp has some angle. And this angle is increased until it first starts to slide. And the question is, at what angle does it start to slide? Well, let's not forget that a slope is somewhere between a horizontal and a vertical situation. Here, the box is definitely going to slide. Here, it's definitely not going to slide. And why? It's because in this situation, the weight is downwards and it slides down. In this situation, the weight is downwards and it is opposed in equal and opposite way by the normal force of the horizontal surface. The difference about a slope, and it's somewhere in between, is because the normal force is 0 here, or at least it's perpendicular, and it wouldn't slow you down falling anyway. The normal force is always perpendicular to the surface. So the normal force is this way, necessarily, and the weight is downwards, necessarily. Now those two are not in direct opposition, but there is still some effect, unlike the vertical situation where N has no effect, and unlike the horizontal situation where N is directly opposed. So, if we want to know, first of all, a box starts to slip when the forces are no longer balanced. And it's just on the edge of slipping when the forces are perfectly in balance, but if there's any change, if there's any more increase. So we're going to look at the maximum situation when the forces are just in balance and it is just starting to slip. Or just holding on, let's say. That's the same situation. So if we need to figure out, this is a problem, all objects are going to accelerate or not depending on the forces on them. Forces, net forces, cause accelerations. F equals ma. Forces can be seen to be independent in 2 dimensions. And that means, let's say, horizontal forces versus vertical forces. Or, in our case, because this is at an angle, the coordinate system that we're going to choose is going to be parallel and perpendicular. I'm going to call this the perpendicular axis, and I'm going to call this the parallel axis. You might want to consider this the y-axis, and this to be the x-axis. The point is, our perspective of horizontal or parallel versus vertical or perpendicular is going to be relative to the slope. It helps us visualize the forces that are either going to pull us up and down the slope or keep us against the slope. All right. So what, if it is just on the edge of moving, but yet hasn't quite moved, the net force is 0. There's forces, all the forces are in balance. It's not yet moving, so we can at least calculate the forces on this the moment before it starts to slip. So let's consider that. What would those forces be? Weight's always there. The normal force is always pushing, and we know what this weight is going to be. This is going to be equal to mg downwards. We know that value. We don't know what n is yet. There's going to be, we're going to look at the point of contact. Forces are pushes and pulls, so we're going to look for forces right here. The box has only one contact point. There's a normal force there, and it's about to slide down the hill, so there's also a friction. And we're going to say that friction is pointing uphill. So there's a friction. And this is the static friction. It hasn't moved yet. So let's remind ourselves what friction is. Friction is equal to mu, the static mu, which we know, and n, which we don't know. I will continue. Well, actually, I still have a few minutes left on this video. So if it's not moving and the net force is 0, that must mean the net force parallel, or I could say x, is equal to 0, and the net force in the perpendicular direction, or the y direction, is equal to 0. And what's the net force? That's the addition of all of the forces. So in the parallel direction, I certainly have the friction force pulling it up. So what is pulling it down? Not n. What's pulling it down is the weight. And as I've warned in other, we need to be able to break, this weight is at an angle into our coordinate system, and all vectors at an angle in your coordinate system can be broken up into a portion that is in one dimension of your coordinate system, in this case, this perpendicular dimension, or the y dimension. So the weight is pulled straight down towards the ground. That means part of the weight is pulling against the hill, and part of the weight is pulling along the hill. Now, these are not new forces. I haven't added new forces. These are components of the weight. So there's the weight. I can put it on the side and erase this at the tip. So there's the weight, and it's pulling down that parallel, down the hill, and it's pulling partially against the hill. So the weight on an angle does two things. It keeps the block against the hill, and it pulls the block down the hill. All right. So in the parallel direction, I have the friction force holding it up the hill, and I have the weight pulling down the hill. And given the coordinate system, down the hill is going to be negative. In the perpendicular direction, I have the weight pulling down and n pushing up. So there's three forces. Two of the forces just have a single direction, and one force has components in two directions. So I have four terms here. The weight has been the friction force is purely parallel to the slope. The normal force is purely perpendicular to the slope, and the weight partially pulls down the slope and partially against the slope. We'll solve those in the next video.